Okay, let's start. So we were talking about we were looking at this parametric function last time, and I started talking about signed area. So remember, signed area in Cartesian coordinates, or rectangular coordinates, back we did a while ago. What was the rate of change of signed area? What was the rate of change of signed area? So if that's my function, f, what's my rate of change of accumulated signed area? The value of the function, right? So where is it accumulating? It's accumulating here on the right side. And so how much does it accumulate by? What's the rate? Well, it's that height right there. Whatever that height is how much more we add on, right? For a little change in x. So that's the rate of change, is the value of the function. So we had that. And we said that this is, essentially, this is the y coordinate. And this is a dx. But we needed to use t because x is where we're at the right side. Okay? And then t is every value from a to x. Right? So we need that other variable that represents x values changing from a all the way to x. Okay, so in parametric, suppose we have x now this t is not the parametric variable, right? This t is just any symbol that we choose to be all the values from a to x. So now this t is our parameter, right? So this t is our parameter. So I'll call it p of t and say q of t. So here we're using t differently, right? So t here is just every value from a to x. And then t here is our parameter. It's our independent variable, right, in the parametric function. Okay, so in parametric, our signed area would be f of, now t, right? It's going to be as a function of our parameter. It's going to be the integral from a to t. And this is a starting t value, right? Starting t value, final t value, and then we need y. So what is the y coordinate, right? So we're going to still have the signed area between the x-axis and the curve, but we're just transforming that into our variable t now, into our variable t, the parameter. So we need y. What is y? It's q, right? I'm calling that q. But then we need a different variable than t, right? So q of, say, yeah, I could use u. I'll use v. So q of v. And then we need dx. What's dx? Well, dx comes from the rate of change of x, right? What's the rate of change of x? P prime. And the meaning of P prime is that given any change in v, given any change in, we're saying v, the change in y is, did I blow, yes, change in x is the rate of change times that change in v, right? So it's just using that meaning for rate of change again. So my dx is going to be P prime of v dv. And so this is the way that we set up signed area between the x-axis and the curve if you have a parametric function. Because this is the same structure as this, y times dx. Okay, so what would happen? So this is something like t equals 1.4 here. And so I'm going to make my a value 1.4. I'm going to start accumulating signed area at 1.4. And as t increases, what will I be doing? So what will happen? As t increases from 1.4, will the value of this function increase or decrease? Why increase? Right, because I'll be moving t. Remember, the direction of the curve is to the right. So as t increases, I'm going right. And my function is in positive x territory. So what will that accumulation look like? As t increases, it'll look like this, right? And it'll keep going. And then what will happen when I see I've got an x-intercept coming up here for a future value of t? So here t is increasing. I'm accumulating signed area. What's going to happen when I get to this x-intercept down there? Does this signed area function for these values of t care anything about this down here? Doesn't even know it's there, right? These are future values of t. It could care less. It just cares about these values of t, and it's going to keep giving me the signed area to the x-axis, right? All right, so I'm still accumulating. T is increasing. T is increasing. Oh, I think this is negative 1.4, because with t was 0 was here. This was negative. Because I think t equals 0 was right here at 1,4. This was t equals 0. 0.1 comma 4. Okay? And so I'm accumulating. Again here. Still accumulating. So what's going to happen then when I get to, I'm accumulating all this area and the signed area. What's going to happen when I get to the bottom point and I start turning around? Oh, I didn't want that. Oh, let's go with this same color that I got. Maybe it'll show up. Let's see. Does this show up?
Yeah.
Same color. Okay? And so then what's going to happen? So I'm going to get to this bottom point here, and as t increases, I'm going to keep accumulating signed area. What's going to happen? So now I'm going to be doing, as t increases this way, so then it's going to what? It's going to accumulate like this, right? Is the signed area going to be increasing or decreasing? Increasing or decreasing? Well, t is increasing, but what is x doing? X is decreasing, and what is dv? Change in x. This is my dx right here. This is p prime v dv. This is my change in x. So what about changes in x? Positive or negative? If x is decreasing, then my changes in x will be negative. So what about the signed area here? So as t increases, x decreases, and dx will be negative. So these values I'll actually be decreasing through there. Okay? So t is increasing the whole time, but because x starts decreasing, so our signed area is going to start going down by the amount of the accumulated orange. So I get to here, this is actually about the t equals positive 1.45, right there, that is for t is positive 1.45. So what is the integral from negative 1.4 to 1.45 of? This is my, so this is f of v. This is my f here. G, no, I need g. G is the y coordinate. Is that on the screen now? F and G? So my y coordinate is g, so it's going to be g of v times f prime of v, this is my dx. F prime of v dv is my dx. So what will this value represent, right? So if I was using my function and I plugged what? It's f of negative 1 or 1.45. F of 1.45, when t reaches 1.45, what will that value represent if this is my signed area function starting from negative 1.4? What will I get? What number will that give me? Yeah. So which? The black that's now showing, right? Because when we accumulated up to 0, we got all that black, even underneath the orange. But then when we started, we kept increasing t to 1.45. What? We lost all the orange. So this is going to give the black shaded area that's still showing, right? It's still showing black. See that? So you end up getting the area inside the curve, above the x-axis. You see that? Now that won't always be the case, but just in this particular case, you end up getting that, what you now see shaded black. You get that area inside. And so now we're going into negative territory. T is increasing. X is what? X is decreasing and y is negative. So if I keep going past 1.45, will I accumulate positive or negative for this down here? That's going to accumulate positive because your x is decreasing, but your y is negative. So negative times a negative is a positive. So it's just screwy things happen, right? So let's do blue. So if I kept going, this would now increase my, would be an increase in my signed area function. Because why? Because x is decreasing, that gives a negative dx, but y is negative, so negative times a negative is positive. So you have kind of screwy things that happen, and you kind of take it case by case. But I just wanted to give you kind of a feeling of what happens with signed area and parametric functions. Any questions? Okay, we're going to move on to the next section. You got homework. There's written homework and online homework due Wednesday morning. Any questions on parametric functions? Okay, so the next topic, last topic of the course. So actually, parametric functions and this last topic are really, really important for Calc 3. Sums and sequences, not so much. You don't really see sums and sequences in Calc 3, but these last 2 weeks of the course, parametric and polar functions, very important in Calc 3. You see it all the time. So this is, we're going to do what's called polar coordinates. So what have we been so far in your math career? When you graph things, it was always in the Cartesian plane, the rectangular coordinates. And what are our rectangular coordinates? What are they? What are our rectangular coordinates? Someone said x and y. That's right, x and y, right? X represents what? What? When we graph, what does x represent? Distance to the right, right? Positive distance to the right, negative, if it's negative, it's distance to the left, right? So rectangular coordinates are x and y. X is distance to the right, y is distance up. Positive distance up. If you're below the horizontal axis, y is a negative value, right? So negative if going down, positive distance up. Okay, polar coordinates, totally different, right? But it's still a way of finding locations in the plane, but totally different than x and y. All right, so here's how it works. Got a little. Polar coordinates are based on Distance from the pole. So now instead of the origin, we call it the pole. So think about like looking down on the Earth, looking down at the North Pole, right? Kind of looks like that, right? So the pole. So distance from the pole as a function of the angle theta. As a function of angle theta. And it's the same theta that you learned in trig, in pre-calc. It's the same theta swept counterclockwise from the positive x-axis. So therefore, polar curves, polar functions have the form r as a function of theta. R as a function of theta. But we'll get to that later. We just got to learn the basics of this, how to plot points, and we'll get to functions later. Okay, so instead of x and y, instead of x is positive to the right, negative to the left, y is positive up, negative down, instead of up and left and right and up and down, we have an angle measure and distance from the pole. So let's see that in action here. So let's do a real quick overview of angle measure. So angle measure, again, start swept counterclockwise from the positive x-axis. And we're going to talk about radians. What are radians? Did you learn what a radian was? Angle measure radians. Well, if you didn't, here we're going to do it right now. So take a circle of any radius. Say 1, 2, 3. Here's my circle of radius 3, from there to there. Okay? And I'm going to take that radius and I'm going to lay it on the circle. I'm going to grab that right there, that length. I'm going to lay that length on the circle. So it'll take me about right there. So that's the same. That's one radius length. Or 3 units long. As an arc on the circle. So we call that's one radius length. It's 3 units long. Make sense? That defines an angle. Right? So that radius length defines an angle. Right? I want that one in between. That one. So do you see how the radius length will define an angle from my starting ray here, straight to the right, and where that radius length ends? Make a ray from the pole through the end of that arc. That angle is 1 radian. That's 1 radian because it cuts off an arc that is 1 radius length. Well, you say, well, that's only for this circle. No, it's not, right? So if I go out to r equals 5, so here's r equals 5, and I take one of those radius lengths from there to there, so there's my r equals 5, and I take that radius length and I lay it on its circle, where will it end? Same place. So that's still 1 radius length, even though the radius is 5. It still represents the same amount of openness of the angle for its circle. So 1 radian of angle measure, what? It's the openness that corresponds to 1 radius length of arc length. If you take the radius, lie it on the circle, you get 1 radius length. That's an amount of openness. We call that 1 radian. So the number of radius lengths is the same number as the number of radians. So there's 1, and then I could go to, so 2 is somewhere, let's do it. Okay. There's 2. So this is 2 radius lengths of arc length. So here was 1, right? Here was 1. Okay, now that's 2. So what's the angle? What's the measure of this angle? 2 radians, because that angle cuts off 2 radius lengths laying on the circle. And then the things they never told you, right?
Yeah.
Okay, what's this? This is 3. Notice that. Does 3 make it halfway around? Not quite. Not quite. Almost. So to get halfway around, you need to go a little bit further than 3. How many radius lengths does it take to go exactly halfway around? 3.14. 15, not point. There's only 1 point. 3.14, 159, etc. So that's where pi comes from. It's exactly how many radius lengths it takes to get halfway around the circle. And so then that amount of openness of a straight angle is pi radians. Because it takes pi, or 3.14159 radius lengths to get exactly halfway around the circle. So that's where pi comes from. Okay, so that's your crash course in angle measure. We're going to need that for polar coordinates because we'll be dealing in radian angle measure. So then what is straight up? What angle measure is straight up? How many radius lengths does it take from the right side of the circle up to the top of the circle? How many radius lengths is that? Pi divided by 2. Okay? That's not just a symbol for the top of the circle. It's a number. Find that. What number is that? Someone put in your calculator. What is pi over 2? 1.57 something. What does that number mean? 1.57. 1.57 what? Radius lengths to go how far in a circle? A quarter of a circle, right? If you take the radius and lay it on the circle, it'll take 1.57 or pi over 2 radius lengths to get to the top of the circle. These angles, pi over 4, pi over 6, 2 pi over 3, 5 pi over 6, they're not symbols for places on the circle. They're not labels. They're numbers. They're a number of radius lengths. That's why it's always good to actually calculate those decimal approximations. You got to think of them as numbers, number of radius lengths, and therefore angle measure in radians. So this openness right here is 1.57 radians because it comes from 1.57 radius lengths laying on the circle to make a quarter circle. And then we got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So this, now you remember all this. But my emphasis now, when you're looking at all those symbols that you learned before, is they're not labels for places. They're actually numbers of radius lengths, and therefore values of radians, openness, and angles. All right. So that's our crash course in angle measure. So back to polar coordinates. So we have theta. Theta is our starting point. So here is, say, theta is 1.87. Okay, here's theta is 1.87. That means 1.87 radius lengths to get around to that spot. And so then in polar coordinates, we start with the angle. And then in that direction, in the direction of theta, think of now your axis, your unit axis for r is in the direction of theta. So now this is the r axis in the direction of theta. So So say R is, say I've got the point theta equals, what would theta equals? 1.97. .87, thank you. And R is 2.2. Okay, but here's the thing. The convention for writing polar points is backwards. Why is it backwards? Because what comes first? What comes first? We're going to sweep an angle first. We're going to sweep an angle first, and then once we sweep that angle, then we're going to head off from the pole the distance of r. So we sweep that angle, that was the 1.87 radians, and then I'm going to start at the pole, and we're going to march out to 2.2, and that's how I'm going to get my point. So I have no idea how this came to be, but it's messed up. It's messed up, okay? The convention is r comma theta, but theta comes first in the process. It's the independent thing. It's the independent. Theta is independent, and then r is dependent. But the convention for writing out points is r first, then theta. You have a question? So this is the point, 2.2, comma, 1.87. So the direction when you head out from the pole in the direction of r, in r units, it's always whatever direction theta you picked. Okay, so let's just do one more here. So okay, here's theta equals 5.71 radians. It puts me in the fourth quadrant. So I want you to write the coordinates of this point right here. What would be the coordinates of that point that I've highlighted? This angle is, what did I say? 5.71? Theta is 5.71. So what would I write first? 5 comma means go 5.71 radians, puts you in the fourth quadrant, that's the angle measure, and then start at the pole and march out 5 units along that ray, the terminal ray of the angle, right? You march out 5 units along the terminal ray of the angle, which is 5.71. Okay, yes please.
Is there still 4 coordinates in the polar?
Is there still what?
4 coordinates.
Quadrants? Yep, we still talk about the same 4 quadrants, yes. We still talk about first, second, third, and fourth quadrants, yep. Okay, so what if I swept this angle measure, and then I had a negative r? What would that be? So if I said negative 3, comma 5.71, where would that be? This is what gets tricky. So 5.71 means sweep 5.71 radians down in the fourth quadrant, and we're pointing down this way, right? We're pointing that way, so what would a negative 3 for r mean? Can you imagine what that would mean? Is that what you were thinking? Negative r would be, just like negative x is in the opposite direction of positive x, negative y is in the opposite direction of positive y, negative r is the opposite direction of positive r. So plot this point. So it would be, this point right here would be the point, what? Negative 3, 5.71. So this is where students, it gets tricky. So you got to really be confident about that direction of positive theta. Always pinpoint that direction of positive theta, and then the direction of, the direction of positive r, which is in the direction of theta, right? Positive r is in the direction of theta, then the direction of negative r is exactly in the opposite direction. Does that make sense? You need practice. So here's some practice points. Oh, could you hand these out, please? Zach, can you help me hand these out? So just leave it. Just leave it. Take one. They're two-sided. They've got graphs on both sides. Pass it down. Bring it to recitation tomorrow. You got 12 blank axes to work on. Bring them to recitation. I've got more if you need more. So here's practice. Okay, I'll just put a couple up by request here. Probably ones with some negatives. All right, which one? By request. We'll do E and F. So E, so we're 7 pi over 4. Which quadrant is 7 pi over 4? Fourth. I think it's right about there. That's 7 pi over 4. Yep. And then, so there's 7 pi over 4, and then that's the direction of positive r in the direction of the terminal side of 7 pi over 4, so negative r is here. There's the point. That's where you should have put the point for E. Negative 4, 7 pi over 4. Okay, last one. So what would a negative angle measure be? Negative angle measure. Clockwise from the positive x-axis. So here's 0. So we're going to go clockwise 5 pi over 6. Where's that? That's right there. One more. It's there. All right, there we go. So there's negative 5 pi over 6. It's swept clockwise from positive x. And then that's our value of direction of positive r. This is my direction of positive r in the direction of negative 5 pi over 6. So negative 2 would be what quadrant? This point right here. That's the point for point F. Negative 5 pi over 6 gives you positive r values this way. Negative r values would be in the exactly the opposite direction. That would be the point for part F. It doesn't make sense. Doesn't make sense. Any other questions? Any other requests on those? Yeah.
Is the negative 5 pi over 6 be the same as negative 5 over 6 would be just like flip the line? Can you like go counterclockwise and then just flip the line?
Okay, so I think what you're getting at is that, so now we've got this point here, and this is the point, negative 2, negative 5 pi over 6. Is there another way to write that point? Is there another way to get to that point using polar coordinates? Tell me. Positive 2 and? Pi 6. Is there another way? Tell me. Is there another way with positive 2? What was it? Positive or negative? Negative, right? Right, so this would be, so I can get to it by going negative 11 pi over 6 with a positive 2 also. Okay? And then I could do negative 11 pi over 6. I could go around one more time clockwise. Wouldn't that take me to the same place? So go around one more time clockwise, which means a negative 2 pi, and then still go positive 2. Is there another way? Yeah, so here's a big difference between plotting in polar and plotting in x and y. Given a point in x and y, there's only one way to express that. There's only one x coordinate that it has and one y coordinate. But in the polar plane, given a point, there's an infinite number of ways to express it. Because you can keep going round and round in circles. I can, do actually minus 2 any multiple. So I can say minus 2 pi k, where k is any positive value. Any whole number. Positive whole number. Yeah, I guess.
Any integer.
Yeah, any integer, right? Any integer, so we can go the other way too, right? Any multiple of 2 pi going around takes us back to positive r being in that direction. You can go 2. Okay, so really important to know that there's lots of different ways to represent the same point in the polar plane. Okay, what if we were to take the polar plane and superimpose it on the polar plane and the xy plane together? So I want to go back to, let's write that point as, let's just go back to, say, 2 and pi over 6. All right, so I'm using this version. So here's my pi over 6 angle, positive 2. So here's this version of that point, 2 pi over 6. How would I get the x and y coordinates for that? What's the x coordinate of that point? Well, it's how far I go out here. What does x equal? Something less than 2, but exactly what? There's my y coordinate. So what does x equal? How would I get that from the polar coordinates? Tristan knows. What's that? Yeah, so this goes back to your trig from pre-calc. You've got the angle measure and the radius, which is the hypotenuse. So the x is just 2 cosine pi over 6. And y is 2 sine pi over 6. So therefore, x is always, for any r theta, x is r cosine theta, y is r sine theta. If we're like kind of transferring back and forth between Cartesian rectangular coordinates and polar coordinates. Usually you're dealing in one or the other, okay? So usually you're dealing in one or the other, but if you want to make the switch, here's how you would switch from polar to x and y. And if I was given x and y and I needed r, how would I get r given x and y? Pythagorean theorem, right? So r squared equals. So this is how we would get r given x and y by the Pythagorean theorem. Because now r is the hypotenuse of the triangle. And then how would we get theta given x and y? So if y is this opposite side here and x is the adjacent side, y over x. So opposite over adjacent is tangent. So theta is arctangent of y over x. But just remember that the range for arctangent is negative pi over 2 to pi over 2. It only gives the angle measure from straight down at negative pi over 2 up to straight up at pi over 2. So if your angle that you're trying to solve for is somewhere else, then you have to adjust the answer you get from arctan. You have to make the adjustment to get the angle that you want. You practiced those and you did those kinds of problems in pre-calc. When you learned about arctangent. Remember? That's a long time ago. Yeah, brush up. All right, so this is given polar coordinates, switching to Cartesian. This is given Cartesian coordinates, switching into polar. All right, so we said that when you sketch polar graphs, we sketch r as a function of theta. So let's do a real simple one to start here. Any questions on that? So let's look at this function here, 2 sine theta. F of theta, or r, is 2 sine theta. So the way that we sketch polar graphs is we're first going to sketch in rectangular coordinates where theta is our independent on the horizontal axis and r is our dependent on the vertical axis. So we need to sketch 2 sine theta. Does that start at the min, the midline, or the max? 2 sine theta. Remember where sine starts at theta equals 0? The midline. And does it go to the min or the max? It goes to the max by pi over 2. It goes to the max, which is what's the max of this function? 2. And then, as theta goes from pi over 2 to pi, it goes from the max to 0, the midline. And then, at 3 pi over 2, it's at -2. And then back at 2 pi, we're back at 0. So we're going to use this graph, the graph we know of sine 2 theta. To graph the polar graph. So just watch what happens. So we're going to think about as theta goes from 0 to pi over 2. As theta goes, let's turn it on here. So as theta goes from 0 to pi over 2, r goes from what to what? Nope, 0 to 2, right? So do you see it happening there? As theta goes from 0 to pi over 2, r goes from 0 to 2. Can you see that black point tick mark on the theta axis there? Or the r axis? So what does that look like as it draws it out?
8.
Here it comes. Ready? Watch. So now it's generating the points there. See that? So again, as theta goes from 0 to pi over 2, r goes from 0 to 2. And then what happens in the next? As theta goes from pi over 2 to pi, r goes from 2 back to 0. And then, as theta goes from pi to 3 pi over 2, where is it going to draw? What quadrant will it draw in? What quadrant will this draw? So theta is going from pi to 3 pi over 2. Our values are negative. What quadrant will that draw the graph in? First quadrant. The positive angles, positive r values will be in the third quadrant. That means negative r values, which is what we have, 0 to -2, will be in the first quadrant. Watch. So watch it happen. See it drawing it? So what does it do? It actually just draws the same points again, but with negative r values. And then, as we go from 3 pi over 2 to 2 pi, it's drawing in the second quadrant, negative r values from -2 to 0. So it actually draws this thing twice. So the question is it a circle? Stay tuned in Wednesday's class. Stay tuned in Wednesday's class.